Hi everyone. Uh, this is Chemistry 105, Chapter 8. In this chapter, the power from energy from electron transfer, we're going to discuss how do we generate electricity from chemical reactions using chemical energy, and how do we store electrons, store electric energies in all kinds of batteries, and how do batteries use in general. And so we're going to go over some brief introduction about these battery topics and take a look at the chemistries involved in these type of batteries. So the same in this chapter. First, we want to go over some questions we want to ask throughout the chapter. First is, what are the main types of batteries and how do they work? And what are the differences between galvanic batteries and electrolytic batteries? So different types of batteries. One, we use chemical reactions to create electricity. One, we use electricity to run some chemistry reactions. And how are batteries recycled, and what are hybrid vehicles and how do they work? And also, are there benefits of using fuel cells instead of gasoline fueled vehicles? And we're going to introduce what are fuel cells as well. So fuel cells as well. So let's take a look. First, what is a battery? Okay, battery is a system in which we convert chemical energy into electrical energy directly. So basically, we convert chemistry reactions into electricity in a directly device. That device is called a battery, or system. That system is called a battery. Now, normally, a battery is composed of individual units. And those individual units are called galvanic cell or voltaic cells. So normally a battery, like here shown in this picture, a nickel-cadmium battery pack, are actually 6 nickel-cadmium galvanic cells wired together to give us a bigger system. We call that a battery. So the basic unit for normally daily we call battery are these individual galvanic or voltaic cells. So you can see here a series of galvanic cells that are wired together constitutes a true battery, like the one in your car, or like the one you have in your portable tools, like this one, nickel-cadmium cells. So let's take a look. What is an individual unit? How does a cell, a galvanic cell, work? Okay, a cell is a unit, a direct device that is the one converts the energy released in a chemical reaction into electricity, into electric energy. And this process, okay, how do we convert a chemistry reaction into electric energy? This process is realized by the transfer of electrons. Remember, if you want electricity, you need electrons movement, and that is realized by the transfer of electrons in our chemical reactions. In our chemical reactions from one substance to another. Okay, as shown in this picture, this is a lab grade or a lab scale galvanic cell or voltaic cell. And you can see that the lab scale has a zinc metal, a copper metal. They're both immersed in the solutions, and they're separated by a membrane or a disc. Okay, there's a link here in your lecture notes. You can take a look as well using some simulations and see how galvanic cells work. But we're going to analyze this lab galvanic cell in detail. Okay, first, as we mentioned, there are 2 metals in this lab galvanic cell. One metal is a zinc metal, another metal is copper metal. Okay, they're both immersed, in their solutions. Okay, in their solutions. Now, for zinc metal, what happens is when they're connected, when zinc metal and copper metal, they're connected, the zinc metal will lose electron. Okay, the zinc metal will lose the electron, and zinc loses 2 electrons to become zinc 2 plus ion. Okay, zinc 2 plus ion is zinc losing 2 electrons. And this process, okay, this process is called the oxidation process, okay, called oxidation. And meanwhile, okay, meanwhile, these 2 electrons will be received by copper 2 plus ion in the copper solution. Okay, copper 2 plus ion in the copper solution. And these 2 electrons will change the copper 2 plus ion into copper metal, which will be deposited on this copper metal here. And this process of receiving electron, of gaining electron, we call the reduction process. So you can see that one metal, zinc, lose electrons gained by another metal ion. So this chemical reaction realized what? The transfer of what? Of 2 electrons. From where? From the zinc all the way to what? To copper. Okay, from the zinc all the way to copper. Again, zinc lose the electrons, and electrons transfer to what? To copper, to be change copper to plus back to copper. So one lose the electron we call oxidation. Another metal ion gains those 2 electrons, we call that reduction. And this process realized electron transfer. Okay, realized electron transfer. Now, here we represent these 2 processes using what? Using chemical equations. As you can see here, zinc lose electrons to become zinc 2 plus ion. These 2 electrons are the one lost, so they're showing as product. And these 2 electrons will be gained by copper 2 plus ion to give copper metal. You can see that because electrons are gained, so electrons are used as a reactant. Now these 2 reactions, okay, these 2 reactions, one is for oxidation, one is for reduction, because they are only showing half of the process, one losing, one gaining. So we call these equations or these 2 reactions half reactions. Okay, half reaction. Of course, zinc, the one losing electrons, is called oxidation half reaction, and copper 2 plus gaining those 2 electrons is called the reduction half reactions. Now, if you add 2 reactions together, that means you add all the reactants together, add all the products together for these 2 half reactions, and you will find out these 2 electrons will be canceled each other because they're both on either side of they're on both sides of the arrow. So you will end up with an overall reaction. Okay, overall reaction. That is what? That is copper 2 plus ion react with zinc metal to give copper metal and zinc 2 plus ion. Okay, you can see that the overall reaction after you add both half reaction together does because electrons. The reason is electrons are canceled because they're on both sides of the arrow. But they do what? They do exist. They are transferred. Transfer from where? From zinc to metal. It's just in the overall reaction, we didn't show that. But the electrons are actually transferred in the overall reaction. Okay, in the overall reaction. Okay. Now, of course, this is our first introduction about reduction and oxidation process, and we give that overall process a word, okay, a man-made word called redox reaction, showing these 2 processes are actually happening together, okay, because if you want some metal to lose electron, you need some another metal ion to gain that electrons so that the electrons can be realized can be transferred. So that's why these 2 processes are always happening together, and that's why we always call them redox reactions. And now here's a link in your notes you can click and understand why Statue of Liberty actually turns green. It actually also involves the transfer of electron, also involves redox reactions. Of course, Statue of Liberty is made of copper, so this redox reaction involves happening between copper metal and the oxygen in the air. Basically, is the electrons transfer from metal to oxygen in the air. So metal will become metal oxides. That is why the statue of liberty turns green. That is the color of copper oxides. Again, you can understand the chemistry inside the story and helping you better understand what is redox reactions. What are redox reactions? Okay, now here are some quick practices. There are 5 half reactions showing here. They ask you, can you, based on what we learned, and quickly decide which reactions is oxidation half reaction, which reaction is reduction half reaction. Now remember we said earlier, oxidation is the process of losing electrons, in which half reaction electrons will be shown as a product. On the other hand, reduction is the process of gaining electrons. So in those half reactions, electrons will be as what? As reactants. So if you take a look, the first reaction is the aluminum metal gain electrons to become aluminum metal ion, gain 3 electrons to become aluminum metal. So this process is what is reduction process. And the second reaction is the same as we shown before. Zinc lose electrons to become zinc ion. So that's oxidation process. This is manganese 7+ ion gains 3 electrons to become manganese 4+. You can see that +7 becomes +4. You gained 3 electrons, and that process is reduction. Okay, number 4 is what? Is water losing electrons to become hydrogen plus ion and oxygen gas and 4 electrons. That's the lost electrons. So D is oxidation reaction. And finally is hydrogen ion gains electrons to become hydrogen gas. And that's reduction. Okay, that's reduction. So A is reduction, B is oxidation, C is reduction, D is oxidation, E is reduction. Okay, reduction reaction. Okay, now if you go back after we studied a lab scale galvanic or voltaic cells, if we take a look, what we mentioned earlier, a nickel cadmium battery, which is made by like nickel cadmium cells, you will have a better understanding, or we can use these reaction as a reinforcement of what we learned about galvanic cells. So if you take a look at nickel cadmium battery or nickel cadmium cells, you'll find out the battery is composed of layers of nickel and cadmium metals. Of course, cadmium metals are in layers of cadmium metals, but nickel exists as actually nickel oxide and hydroxide, basically existing as nickel ions, okay, nickel ions. And the transfer of electrons is actually from cadmium, okay, the transfer of electrons is actually from cadmium metal to, from cadmium metal to nickel, okay, cadmium nickel, and that's the transfer of electrons. Okay, if that's the case, we know that cadmium will be losing electrons. Here are the half reactions. Cadmium losing electrons become cadmium 2+, losing 2 electrons. And now nickel, in which nickel exists as nickel 3+ in nickel cadmium cell. So nickel 3+ gain electron to become nickel 2+. So that means each nickel 3+ only gains 1 electron, if you notice that. But remember, in the oxidation half reaction, cadmium lost 2 electrons. So in order to gain both the electrons from cadmium, there needs to be 2 nickel 3+ to receive 2 electrons to become 2 nickel 2+. Okay, because that's how the half reaction works. For nickel, only gains 1 electron. So in order to gain 2 electrons, you need to change the coefficient to 2 for the nickel half reactions. And now cadmium losing 2, nickel gain 2. If we add both reactions together, you will get the overall reaction basically is cadmium transfer electrons to 2 nickel 3+, then 2 nickel 3+ becomes 2 nickel 2+, and cadmium becomes cadmium 2+. So that's what happens for a nickel cadmium bell or cell or cadmium battery. And this is what we talked about earlier. The cadmium releases 2 electrons, become cadmium 2+, but nickel ion 3+ gains only 1 electron to become nickel 2+. So that means you need a 2 nickel 3+ ion to receive or accept those 2 electrons from cadmium. okay, from cadmium. But again, for cadmium, losing electron, this process is called oxidation, and nickel gains electrons, that process is called oxidation. And as we shown before, the overall reaction, you do not see electrons because electrons got canceled on both sides of the arrow. Okay, so here are some fundamental mnemonics. Okay, mnemonics ask you to memorize the terms in the oxidation and the redox, or called redox processes. Oxidation is the lose of electrons. Reduction is the gain of electrons. Or you can say loss of electron is oxidation, gain of electron is reduction. It's Leo the Leon says Ger. Okay, again, these are mnemonics helping to memorize the terms in the redox reactions. Okay, redox reaction. And here is the link for redox reactions or some experiments. Okay, move up. Now, you already see that some metals like cadmium lose electron, become cadmium 2+, but nickel will change from 3+ to 2+. So you may wonder, what are the how do we know? Okay, how do we know what oxidation states? Okay, what oxidation state do these metals have? Okay, do these metals have? That depends, but this chart shows you some of the oxidation states for metals in our periodic table. Okay, periodic table. Normally the metals will lose the electrons to become what? To become positively charged. You can see that metal normally have positive oxidation states, but the non-metals on this side of the periodic table will normally have what? Have negative oxidation state, because non-metal will gain electrons. But in order to know what oxidation state each metal has, we have to look into different types of batteries, which we're going to see in the later in a few minutes in the later of this class lecture. Okay, so remember, in a cadmium nickel cadmium cell, the transfer of electrons is from cadmium to nickel. Okay, to realize the electron transfer to give electricity. But again, because we're talking about battery, the transfer of electrons is actually not internal. If you look at the battery, where later on we're going to study as well, the cadmium and the nickel part of the chemical substances are actually separated, okay, separated in a battery by some separators. So the transfer of electron is not realized internally. The transfer of electrons is actually through what? Through the wire, external circuit, okay, external wire. That transfer of electrons through the external circuit actually produces electricity, because you're talking about flow of electrons from one region all the way outside the external to another region of the battery. That's how electricity is produced, through external transfer of electrons, but still transfer from one substance of inside the battery to another substances. And of course, the direction of electron transfer is directed or driven by the potential of electrons. Electrons will go from higher potential to lower potential, just like water. And that potential difference is called the voltage. Okay, we're going to talk a few more words in the next couple of minutes about voltage as well. Okay, so now, in order to realize that transfer, enable the transfer of electrons, so the half reactions, okay, the half reaction must be placed on some metal sites, okay, on some metal conductors, okay, metal conductors for the redox reaction, for the oxidation and the reduction reaction to happen. And those metal conductors, where the chemical reactions are actually happening inside a battery, are called electrodes. Okay, are called electrodes. That's how, because they must be metal conductors. And those electrodes are where the redox reaction are happening. Now, because in a battery, we have oxidation, losing electrons, and reduction, gaining electrons. So we have two types of reaction happening. So in a battery, we have two types of electrodes. Okay, electrodes. In nickel cadmium battery, for example, the nickel loses electrons. That's where the oxidation happens. That's where the electrons are coming from, because nickel loses electrons. That's where the electrons are coming from. So we call the source of electrons where the oxidation happens is called the anode of the reaction. Okay, the anode of the reaction. And on the other hand, where the electrons are received, okay, where the electrons are received, or where ox reduction happens, okay, where electrons are again received, is called the cathode of the reaction. So very important two terms. Anode is where the electrons are coming from, oxidation. Cathode, where electrons are received, are called reduction happens. Okay, reduction happens. And cathode and anode are both the electrodes where the electrons or reactions are happening. And of course, in this picture also shows that to increase the surface area of electrodes, the components inside the batteries are actually layered. Okay, you guys see layers of anode and materials and cathode materials. And of course, electrons are from cathode to what? All the way transferred to the electrons are from anode all the way through external circuit to the cathode. Okay, because anode has more electrons, is the higher electron potential all the way through the external cathode. And the difference between these two electrodes, the potential difference, is called the voltage of the battery or the voltage of the galvanic cell. So here is the voltage. Now you know what is voltage. Voltage is the potential difference between the anode and cathode. Of course, anode, the source of electrons have higher potential. Okay, and the units for voltage is volts. Okay, is volts. Now a few extra words about voltage. Okay, voltage is the potential difference of anode and cathode. So the voltage is a function of the chemical is involved. So basically determined by what chemicals you're talking about in cathode and anode. Once you have a chemical set in a battery, then the voltage is set. Okay, voltage because the potential is determined by the difference between anode and cathode. It is determined by the chemical composition of the battery. And because of that, the cell voltage is not a function of the size of the cell. Okay, that means larger cells, even though it contains more materials than smaller cells of the same type, but the difference of potential will be the same. Okay, that means the voltage will be the same for the same cell of the same materials. Okay, and if size is better, meaning it will transfer more electrons, it will last longer, it will transfer more electrons. But the voltage is determined by the chemical composition of the cell. So for example, the alkaline batteries you use every day, the dry batteries in your everyday life, they're all the same type. Okay, they're all the same type. Later on, we're going to talk about what their chemical composition is. So for example, AAA battery, AA battery, even quadruple battery or D size, C size, they're basically the same type. That means their voltage will be the same, except D size, which is larger, contains more chemicals, will last longer than AAA size, but their voltage will be the same. Okay, voltage will be the same. So finally, we want to review some of the terminologies throughout so far about batteries and about the galvanic cells. Again, a battery is a few galvanic cells wired together. The basic unit of a battery are called galvanic cells. In this picture, is a picture of what? Of a lab galvanic cell. And we know in a cell, there are two half reactions. Okay, half reactions. One half reaction is where the oxidation happens, in which zinc metal loses electrons. And we call the zinc metal, the conductor of zinc metal, the anode. Okay, because zinc loses electrons, is where electron is coming from. And electrons lost from zinc will be transferred from outside the external circuit all the way to the copper metal, which is the cathode. And at the surface of the copper metal, you can see that the electrons will be gained by the copper 2+ ion in the solution. You can see copper 2+ gain these electrons, then become copper metal, will be deposited onto the copper metal surface. So basically, eventually, okay, zinc is losing electrons, copper gaining electrons to become copper. So eventually, you can see that the zinc metal, the zinc electrode, will become smaller and smaller and smaller because zinc is losing electrons to become zinc ion. zinc ion won't be dissolving in the solution. But copper is getting more and more because copper 2+ is getting electrons and deposited onto the copper metal surface. So copper is actually getting more and more the copper electrode. But again, both are called electrodes. The zinc electrode is called the anode, losing electrons, and copper cathode is where the copper 2+ gained those 2 electrons. And the transfer of electrons is through what? External circuit. Okay, external circuit. Okay, again, this picture, very nice, showing you what's going on. The zinc lose electron becomes zinc metal ion to be dissolved in the solution. That's why the zinc becomes smaller. And copper metal ion gains those electrons to be deposited on the copper metal surface. That's why you can see the copper electrode is getting bigger and thicker. Okay, now after that, let's take a look at some of the common galvanic cells we use and we basically encounter in our daily lives. Okay, this chart shows you some common galvanic cells, including nickel cadmium cell. Okay, nickel cadmium cell, the voltage is around 1.25, and it is a rechargeable cell. Later on, we're going to talk briefly what makes a battery rechargeable. And normally, nickel cadmium cell is in power tools, digital cameras, and toys, etc. Another cell is called the nickel metal hydride cell. The voltage is the same, 1.25. It's also chargeable. Okay, nickel metal hydride cells are replacing nickel cadmium for the uses in consumer devices. And also nickel metal hydride cells are actually used in hybrid vehicles. Okay, the third, of course, is the most commonly used cell. It's called alkaline cell or alkaline battery, because one cell is one battery for alkaline cells, and the voltage is 1.5. Alkaline battery is not rechargeable, and alkaline batteries are used in everywhere in our everyday life, right? Flashlights, small appliances, calculators, audio and video remote controls, okay, and toys. Okay, and next one is lithium battery. Okay, lithium battery are used in smoke alarms, watches, LED lights, etc. And also lead acid battery. Okay, the voltage is around 2 volts and also rechargeable. And that is the one in our vehicles. Okay, the one sometimes your battery died in your car. That battery is called lead acid battery. And the one we replaced the big box is a lead acid battery, actually composed of six lead acid cells. And finally is lithium ion or lithium polymer cells. The voltage is 3.6, and they're actually more and more popularly used in laptops, cell phones, and other electronic devices. You're holding lithium ion batteries or lithium polymer batteries. Okay. Now, after that, let's take a look at those commonly seen and commonly encountered galvanic cells. The first one, of course, again, the most commonly seen one, the alkaline battery. Okay, alkaline battery looks like this. It has a plate at the bottom. Okay, the plate and bottom, which is called the negative plate where the electron is coming from. But the real anode, okay, the real anode is the zinc metal. Okay, the zinc metal wrapped around the battery. That's why if you peel off the battery label, you will see the shiny metal. That's zinc metal actually wrapped around the battery. And that is the anode where electron is coming from. You can see that zinc lose the electrons to become zinc 2+. Of course, because it's alkaline, means there are potassium hydroxide paste inside the alkaline battery. So after zinc metal loses electrons, zinc 2+ will combine with hydroxide ions to become zinc hydroxide. Okay, zinc hydroxide, and of course, losing electrons. And those losing electrons will be used by you in a flashlight, in a remote control, and then will be gained by manganese 4 oxide paste inside the battery. And where the electrons is gained is the cathode of the battery is actually the graphite rod at the center of the battery. Okay, you can see the center of the battery is a graphite. That's the cathode. That's where the manganese 4 oxide receives those 2 electrons from zinc. So after manganese receive those 2 electrons, manganese 4 oxide becomes manganese 3 oxide. So each manganese receive 1 electrons. So that's why you have a 2 in front of manganese 4 oxide. And this process will release 2 hydroxide ions. So basically, the amount of hydroxide ions will remain constant because zinc needs 2 hydroxide and manganese will release 2 hydroxide. So inside the potassium hydroxide paste normally remains constant. Okay, and the overall reaction is shown here. Basically, is the zinc transfer electrons to manganese and to realize the electron transfer. Of course, the battery is not chargeable. Okay, not a charge. But again, the anode is the zinc. The cathode is the graphite, where the manganese oxide paste receives the electrons from zinc. Okay, next is the nickel cadmium battery. We have seen multiple times this class, but before now, all the reactions shown before are actually the simplified version. Here is the complete version of the complete reactions for nickel cadmium battery. So for example, the cadmium loses electrons. Cadmium doesn't become cadmium 2+ ion free. Cadmium actually combine with 2 hydroxide ions to become cadmium hydroxide. Okay, cadmium hydroxide. So that means the separator, you can see that the separator are actually potassium hydroxide paste, which provide hydroxide ions to combine with cadmium 2+ ion. And nickel 3+ exists as nickel oxide hydroxide solid in the cathode plate. And after gaining electrons, nickel oxide hydroxide becomes nickel hydroxide. Okay, charge 3 here of nickel. After that, charge becomes 2. Okay, that's why you balance with a subscript of 2. And of course, release 2 hydroxide ions. So overall, the amount of the potassium hydroxide paste does not change, but that shows the anode and cathode reaction. And overall reaction is shown here. Nickel receives electron from cadmium, and of course, the reaction needs water as well in this process. Okay, but the difference between nickel cadmium battery and alkaline battery is nickel cadmium batteries are rechargeable. Okay, rechargeable. And here are some practice. Here are some practice based on the reaction I've just shown you. I think you can manage working on these reactions, especially considering a few facts about. Even sometimes before that we did not bring it up, but I think you can consider some facts we learn about chemical equations, such as whether in those half reactions and overall reaction, whether the mass is balanced. That means you have equal number of atoms on both sides of the same element, or also for those half reactions and overall reactions, are the charges also balanced. For example, on the oxidation reaction, you can see that on the left side, there is a -2 charge because 2 of hydroxide. And on the right side, there is also -2 charge because of 2 electrons. So in a half reaction, you can see that the charge is actually also balanced, not just the mass. But here, I want you to use this your turn 8.3 to practice, where some get to look deep into these half reactions, overreaction, to see that are those reactions, even though they're new, something new concept we learned in this chapter about half and overall, but those reactions still follow what we have studied before about balancing chemical equations. Not only you need to balance the mass, but also you need to balance the charge. Okay, and also if I give you a reaction in this chapter, how can you distinguish between a half reaction and an overreaction? So here are some practice for you to think about using the full reactions inside a nickel cadmium cell. Okay, next is a few words about a rechargeable battery. Like we mentioned earlier, nickel cadmium battery cell is rechargeable. That means if you apply electricity to the cell, the products for nickel cadmium battery will turn back to the reactants. Okay, that's what we call recharging process. And the same, if cadmium lose electrons, transfer electron is called discharging process. So the reaction is basically what? Reversible. Now, that's not a a most important, of course, the reaction is reversible is one of the factors to consider for a rechargeable cell, but there are some technical factors needs to be satisfied in order for a battery to be rechargeable. One factor is both reactants and products must be solids, okay, must be solids in order for a factor reaction to be rechargeable. For example, here you can see nickel, oxides, hydroxide, cadmium, and metal, and cadmium oxide and nickel hydroxides are all solids. Okay, and not only that, the solid products must cling to a stainless steel grid within the battery rather than dispersing. That means they have to be on the metal plate or grid so that they can be rechargeable. And if the voltage is applied to the grid, these products can be converted back to reactants. So these two are actually very important factors to be considered when you manufacture a rechargeable battery, not just the chemical reaction that are reversible. Of course, eventually the accumulation of impurities, breakdown of the separator, eventually the and also some unwanted side reactions of or byproducts. Eventually, the life of a rechargeable battery will be shortened and shortened. Eventually, will end its useful life for any rechargeable batteries. Okay, next is another common battery called lead acid battery. Okay, lead acid battery, like we said, are the one that you carry that every day in your vehicle. They are the workhorse of today's rechargeable batteries. Okay, a true battery of lead acid, the one in your car, like a big box, black box, consists of a series of 6 lead acid cells. Okay, remember we said in the table, lead acid cell has a voltage of 2.1, around 2. 6 of them, the voltage is 12 volt. That is why somebody called it as a 12 volt battery. That is actually 6 lead acid batteries are wired together. Of course, the battery, okay, lead acid battery means it consists of the lead and consists of acid. Here is the overall reaction. You can see that. Okay, you can see that the lead consists of lead metal and also lead 4 oxides. Okay, lead oxide. The acid is actually sulfuric acid. It's fairly concentrated sulfuric acid in lead acid battery. We also call the battery, call the acid battery acid, sulfuric acid. It's 6 molar sulfuric acid. Now, the metal electrodes and also the lead 4 oxides are all on the plate, okay, on the lead grids and filled with like a metal plates. You can see that they're filled with on metal plates. Okay, that is also a factor that to be considered. Lead acid batteries are rechargeable. Now, in a discharging process, of course, lead will lose electrons. Okay, lose electrons to lead 4 oxide. So after that, both lead and lead 4 oxide will be turned into lead 2 sulfate because they're immersed in lead in sulfuric acid. Sulfuric acid has a lot of sulfate ions. So we can see that one has a 0 charge, one has a 4 charge, but once one lose electrons to get the 4 charge one, both 0 charge and 4 charge will become 2 plus charge. Okay, 0 becomes 2. Plus 4 becomes plus 2. 1 charge increase, 1 charge decrease. They all becomes 2 plus charge. And of course, lead 2 plus are not free. They combine with sulfate from sulfuric acid to become lead sulfate, which is also a solid on the plate. Of course, after you apply to electricity, like you're braking, your car is you step on your brake, you're driving. Sometimes they will charge the battery. So the lead sulfate will change back to lead and lead 4 oxide. And that's how the battery becomes rechargeable. Okay, battery rechargeable. And here are some other applications of lead acid battery. They're not only just in your car, but also in some small devices or some small application, like a electric shopping car or some electric toy car, and or even some golf cars. Okay. And finally, is the one we hold in our hands, we use in front of a desk, lithium-ion batteries. They're very commonly, again, used in laptops and cell phones. Lithium-ion battery are also rechargeable. Okay, they're composed of lithium metal, okay, lithium metal, graphite, and cobalt oxide, okay, cobalt oxide. And you can see here, lithium-ion batteries, the lithium ion, the reason it gets the name lithium ion battery is lithium ion simply shuffles okay, shuttles back and forth between these two electrodes. Okay, the anode is carbon graphite. Okay, the cathode are basically cobalt oxide. Okay, cobalt oxide. So what happens is when you discharge, okay, the lithium will lose electron. The lithium metal will lose electron to become what? Become electron and lithium ion. Okay, lithium ion. And then the lithium ion electron will shuttle to the cathode, in which lithium ion will gain that electrons to turn back to what? To back to lithium. Of course, the lithium receiving the electrons are not at the anode side, but on the cathode side, which is what? Which is cobalt oxide. Okay, it's actually lithium doped cobalt oxide. Okay, you can see these are cobalt oxides. Lithium ion gains electrons over there. And when you recharge, lithium ion will travel back. Okay, travel back to anode and to what? To lose electron again. So basically, lithium ion is keeping back and forth between anode and cathode. When you discharge, lithium lose electrons, will be shuttled to cathode, where it gains electrons to become lithium metal again inside the cobalt oxide. Okay, and for charging, of course, these reactions will run in opposite directions. So that's basically how a lithium-ion battery works. Okay, and it can, of course, because both anode and cathodes are solid, and lithium-ion batteries are rechargeable. Okay, rechargeable. Okay, next, we want to talk briefly about one of the uses. Okay, one of the uses for batteries nowadays, and also one of the trend, is the use of battery in our daily drivers, in our vehicles. And if we have a vehicle in combination of both gasoline and the battery technologies, we call those vehicles hybrid vehicles, okay, HEVs, okay, HEVs. Now, of course, because they have both battery and gasoline technologies, in some low speed, for example, the power will be from the battery instead of burning gasoline all the time. So unlike gasoline-powered cars, conventionally gasoline-powered cars, the HEVs will normally deliver better mileage, especially in cities, because in low speed, the power can be completely from charged batteries, okay, charged batteries. And here are some data showing you the miles per gallon, the gas mileage for HEVs. You can see that these are HEVs, means combining, we have a battery and we have a power, we have gasoline engine. And of course, while you're driving gasoline engine, you're braking, the battery will be charged. So you can see that normally the HEVs, and these are some brands, model and make and models from different car companies, have very high city and highway mileages. And another type of EV is called a plug-in HEV. The difference is these batteries is still a combination of battery and gasoline technology, but the batteries in this PHEVs can be charged as well. Okay, so basically after you get home, you plug in the car, you charge the battery. The battery is not a main battery, it's a relatively small battery, but it has a supplied battery that can be charged. So that means it will have stored more energy than you purely just charge the battery by driving. So you can actually charge at home. That's what we call plug-in HEVs. And those cars, okay, those cars have even higher miles per gallon gas mileages. You can see around 80 or 70 or 80 or 90. Okay, and finally, if a car does not have any conventional gas engines at all, just pure powered by a larger battery, by a main battery, and we call those vehicles EVs or electric vehicles, such as Tesla, such as Tesla Model 3, Tesla Model S, Hyundai Kona, or Chevrolet Bolt. Okay, these are pure EV powered, electric powered, and those gas mileage will be extremely high. Of course, that's a converted gas mileage because you don't actually burn gas. Okay, burn gas. They're just converted how much kWh of electricity means a gallon of gasoline. Okay, and this chart shows you the trend of using batteries in vehicles. Okay, in vehicles, and this chart shows you the PHEV means the plugged-in hybrid EVs sales worldwide. And you can see that some countries have increasing sales amount. Okay, new electric seal, for example, China, Europe, and United States. The sales is increasing yearly from 2013 to 2017. That's, I mean, still a long time ago, but this is the chart we have in our textbook. But if you consider the percentage of increase, okay, percentage of increase, Norway, okay, here shown here, you can see this is the percent of increase. Norway, United Kingdom, okay, Germany, and this is Germany, and another one is United Kingdom, I think. Let me see. The Norway is this is Norway, and United Kingdom is here, dark one. I think United Kingdom and Germany. These three countries have the highest increase. Okay, most significant increase of percentage of sales. Okay, number of sales, of course, is China, Europe, and the United States. But for countries has the highest increase of percentage are these three countries. And of course, partly because of the policy from Europe, they are increasing more and more about decreasing the use dependence on gasoline and increase the percentage of battery powered vehicles. Okay, and next we want to talk about metals in batteries and also some recycling issues. If you guys remember that so far we have seen many types of galvanic cells, okay, including alkaline battery, lead acid battery, nickel cadmium battery, and lithium ion battery. All these batteries, they involve the use of what? Metals. Metals are very, very important for battery manufacturing. And because of that, we're dealing with not only recycling issues, but also dealing with, are there any problems of, or is the cost of harvesting or manufacturing these metals gonna increase or decrease? And we're gonna facing the manufacturing problems as well. So here are some questions to think, for you to think about, or for you to search answer to from the internet. What can you do to keep the metals used in batteries from being lost in landfill? The answer depends on battery type. So search the internet and find the answers for the following questions. Well, the first one is, what types of batteries are most commonly recycled? Okay, think about in your daily use, what batteries are you normally recycling and what are not? Okay, are rechargeable batteries you recycle the most, or non-rechargeable batteries? Number two is, why is recycling nickel cadmium battery more critical than recycling an alkaline battery? Okay, think about not just the cost of the nickel cadmium battery, and are there any environmental issue involved in these two metals, nickel and cadmium? And number three is, list some reasons why household battery recycling program have not been as effective as those for recycling car batteries. Okay, you know, a lead acid battery from your car is recycling very good because what? Mostly because when you buy a new battery, the dealer or a AutoZone, these stores will take the battery for you for recycling. You don't have to personally recycle those batteries because normally they will either trade in your battery or just keep your old battery unless you request it. So there may be other reasons, and for you to think about why household recycling is not executed as effective as recycling your car batteries. Okay, I think they're very good questions to think, not just to think about, but try to search for answers. Okay, and next, this is a periodic table American Chemical Society published in 2015 are for labels for labeling those metals. Okay, those metals, not just metals, for labeling the elements that are endangered. Okay, endangered means they're distinct. Metals normally do not extinct, but metals that are increasing the cost, okay, or we have increasing the use of them, or we have limited availability or short of supply, etc. So those are called endangered. As you can see here, the blue ones, okay, the blue ones are ones to consider in the future. They may have a risk to supply because they now have relative limited availability. And the orange ones are increasing, ones have rising threat from increasing use. For example, one of the here, which is not related to battery, of course, we learn in chapter 7 that uranium is what is used in power plants, okay, nuclear power plants, and also nuclear weapons. So they're rising threat from increasing use. And the red ones, of course, are the one in serious threat in the next 100 years, including, you can see that these metals, okay, these metals are, some of them are actually used a lot in batteries: silver, zinc, gallium, gadolinium, arsenic, and also hydrogen and tellurium. Okay, so these are some info from American Society showing you what elements will have limited availability now and also in the near future. Okay, and of course, something to think about as well, especially for metals, we're talking about this chapter, is that really a metal going to extinct? Of course, like we said earlier, endangered doesn't mean the metal is going to extinct, because we know that in chemical reactions, atoms don't really change, right? Atoms do not really change from one to another. Atoms never will be created or destroyed in chemical reactions. So in that sense, metals won't become extinct. But what does it mean when a metal becomes endangered? There must be a reason, okay? And also, since we're talking about batteries, which of the highlighted elements above are currently in demand, okay, in demand for batteries, for fuel cells, for supercapacitors, okay? And also, are there any non-highlighted elements that are currently being used or tested for future use? Do you know that some new technologies, recent development in battery technology, what are some other elements that are not endangered but currently being tested? So in the future, they may be in high demand as well. Okay, and with that, I want to spend a few more slides to talk about one of the metal we are in very high demand, that is the lithium metal. Because remember, lithium metal, not only they're used in our personal devices, cell phones, laptops, but they're actually increasingly used more and more in what? In making hybrid vehicles or electric vehicles as the main batteries. So there are a few questions you may wonder. What makes lithium batteries? Okay, what makes lithium so special? Okay, what property does lithium have that makes it an ideal metal for new batteries than the rest of the metals in the same group? And also, where can we obtain lithium metals? So here are some questions to raise. And of course, we know that, okay, lithium metal is in the very left side of the periodic table. It is in the first group of our periodic table, and we call those metals alkaline metals. And those metals are all very active. So they're perfect metals for battery, right? Because they lose electrons easily because of their first group. However, lithium has very obvious apparent advantages over other metals, because not only lithium is active, but also lithium atoms are small and light, okay, light. And that lightweight is the huge advantage for lithium become the most commonly or demanding metal for building batteries for portable devices. Because remember, imagine you're holding something as light as possible. Okay, and but there's also a problem. Lithium is far less abundant than the other metals, than the other members of the alkaline metal group, than sodium or potassium. Lithium usually deposits are found in remote locations. Okay, and present lithium is mainly mined from salt lakes that once were actually ancient seabed. Okay, remote lakes that contains lithium salt. Of course, this picture shows you active lithium is stored in oil to avoid contact with air and moisture in the air. And also, you can see that lithium metal even floats in oil, evidencing what? Lithium has very low density, that is lightweight, and lithium atoms are small. Okay, here the picture shows you one of the world's largest lithium deposit, a salt lake in a desert area of Chile. Okay, you can see that in this lake, lithium is in the form of soluble salts, lithium chloride and lithium carbonate. Okay, next. Okay, next, this chart, this graph shows you a concept called energy density. Okay, energy density that relates both to the number of ions stored in the electrode and the weight or volume of the battery. So basically, you can see this chart. If the property of the battery is located on the right up corner of the chart, it shows the battery has both small size and lightweight. So size and weight are both relatively small. Okay, and because of that, we call that battery has high density, high energy density, because the same number of ions and their weight and size and both can be small. And you can see that compared to lithium batteries, lithium ion, lithium polymer batteries, the lead acid batteries is either big and heavy because of the metal lead. You know, the metal lead is a heavy metal. So lead acid batteries are usually big, and then that's why we don't carry lead acid batteries with our portable device. Instead, lead acid batteries are workhorses in our vehicles. Okay, so this picture also shows that lithium batteries have high density and also relatively small size and lightweight. Okay, lightweight. And one topic about lithium battery is something you may have heard a lot, including Tesla cars, for example. A lot in news or social media is there's a chance, and including early years, if you guys remember Samsung phones, right? Samsung Note 7, I remember. We can double check. Batteries can catch fire, right? Catch fire can cause some severe damage or accident. So what causes battery fires? Okay, lithium, especially lithium metal. Okay, lithium metal. The metals in group 1, okay, such as lithium, sodium, they are active metals. They themselves, okay, are very reactive towards oxygen and water and even nitrogen. Okay, nitrogen. So non-aqueous. So in order to prevent the contact of especially water, non-aqueous electrolytes must be used in lithium-ion batteries, and the battery packs must be sealed to prevent the exposure to air. And fires are initiated if the separator between electrodes components are broken. So if the separated component broken, which will generate short circuit and major heat, and that will cause what? That will cause explosion of the battery or fire, because if the separator breaks, the reactants are reacting together, will produce not only heat but also too much heat in a sealed area, which will cause explosion. Okay, so here is another link to learn more about what makes smartphones explode, what contains lithium-ion batteries. Okay, and here is a practice. Okay, there's a practice asking you, based on what we learned about metals, okay, based on what we learned about redox reaction, kind of like a review practice. Okay, here we can work through quickly together. Our first one, name 3 attributes that distinguish a metal from a non-metal. Okay, we talked about this topic in chapter 1. Okay, in chapter 1, metals are normally shiny. Okay, they're malleable. They can be made into different shapes, and normally metal conducts electricity and heat very well. Non-metals are elements that don't have those properties. Non-metals are brittle normally. They are either solid, liquid, and gas. And also non-metals normally do not conduct electricity. Okay, so that's 3 attributes that distinguish metal from a non-metal. Number 2 is, here is a reaction showing how do you produce nickel metal from the ore of nickel sulfide. Okay, nickel sulfide basically is you react nickel sulfide with oxygen so that you free the nickel metal. And the question is for here is, do you think in this reaction, nickel is oxidized or reduced? Okay, in order to answer the question, you have to know what is the charge of this nickel in sulfide. Okay, if you remember what we studied before, sulfur, it normally carries -2 charge in a compound. We studied in chapter 5. So in nickel sulfide, this nickel contains a 2+ charge because sulfur is -2. Okay, sulfur is -2. And so the compound of this nickel sulfide is actually more correctly called nickel 2 sulfide. And because of that, this nickel is existing as a nickel 2+ ion. So in order for nickel 2+ to become a nickel metal, you have to what? You have to gain some electrons because you have 2+ charge. In order to put 2+ to become 0 charge of metal, you have to gain electrons. So in this process, the nickel gains electrons. That means nickel is what? Is reduced. Okay, so in the manufacture of elemental nickel process, nickel is actually reduced. Okay, nickel is actually reduced. Now, C is ask you to write a chemical reaction similar for cadmium. Okay, similar for cadmium, and I have the key here for you to take a look, and you can try the reaction by yourself and see if you did it right. Okay, I won't go over that here now. Okay. Now, next, when we talk about batteries, okay, when we talk about batteries, normally we know that, okay, the battery or galvanic cell is a device in which reactants, products are inside the device, okay, inside the device, and of course, reactants themselves will realize a transfer of electrons so that we have electricity, okay, electricity. But one of the big features of all the galvanic cell or batteries we have studied before are the reactants. The reactants and products are already placed inside the device, inside the battery, no matter galvanic, no matter lithium-ion battery, lead acid battery, and alkaline battery. You see that it's a wrapped up device or sealed device. So that's a typical galvanic cell. But now we're going to study a same but different types of galvanic cell in which the reactants are not pre-installed into the battery, but actually keep fueled inside the battery. Okay, and we call that cell a fuel cell. So what is a fuel cell? Fuel cell is still a galvanic cell. Okay, galvanic means what? Converting chemical energy into electricity is the same concept, but the difference is in the fuel cell. Okay, in the fuel cell, the fuel will be filled into the battery, okay, into the battery continuously instead of a pre-installed inside a battery. And of course, the reactants, okay, because they're called fuel, the reactants are actually fuel you can burn. But in a fuel cell, we don't burn the fuel. We run the reaction inside a galvanic cell to produce electric energy instead of burning the cell to produce heat, but instead of burning the fuel to produce the heat. So again, fuel cell is the cell to produce electricity by converting the chemical energy of fuel directly into electricity without burning it. Okay, without burning it. Now, unlike conventional batteries, like we said earlier, fuel cells operate on an external supply of fuel. Okay, that means the fuel is not put into the battery initially. It's kept fueling, kept getting into the battery. And of course, in order to oxidize the fuel, to burn the fuel, not burn the fuel, but convert the fuel into electricity, you also need some oxidizer. The most commonly seen oxidizer is oxygen gas from the air. So that means you also need an external supply of the air or other oxidant materials, okay, because they are keep fueling. Okay, you keep adding fuel constantly. So this battery don't run down or need to be recharged because what? Because you're keeping supplying the reactants. That's a big difference between what we're about to learn for fuel cell. Okay, fuel cell. Now, one of the most developed fuel cell is called hydrogen fuel cell, in which what? The fuel is hydrogen, okay, hydrogen. So first, let's take a look what reactions we're looking at for hydrogen fuel cell. Then we look at a scheme, what is the principle of or how does a hydrogen fuel cell works, okay? First is hydrogen gas in a hydrogen fuel cell will lose electron to become hydrogen 2 plus, okay, 2 plus, and of course, electrons, okay, electrons. And this is the fuel, hydrogen gas. Remember, hydrogen gas can burn actually, but here we're not burning hydrogen gas. We're burning fuel, or we're working on the fuel hydrogen inside the fuel cell. Hydrogen lose electrons, we call the electrode anode. Okay, so this is the anode half reaction. On the other hand, the electrons from hydrogen will be gained by oxygen, okay, gained by oxygen. And meanwhile, the hydrogen plus ion from the anode will also be present here to combine with the oxygen, gain the electrons to turn it into what? Turn it into water. And because the oxygen gained the electrons, we call this electrode the cathode, okay, the cathode. And the product for cathode is water. So if you add these two half equations or half reaction together, you get this. Okay, add all the reactants and all the products together. Then we cancel the ones that are present on both sides. You can see we can cancel hydrogen ions. We can cancel the electrons that are present on both sides of the arrow. What we got is what? What we got is the reaction of hydrogen and oxygen to produce water. Basically, it's the same reaction as if you were burning hydrogen gas. Burning hydrogen gas is the same reaction. But here, because the reaction happened in a cell, we don't see any flames. We only have little heat. We don't need to supply or produce any combustion. We don't need to ignite the whole thing. We basically run the reaction smoothly, heatless or flameless, and of course, the energy produced will be electricity. So here, this page shows you the equations, not only the half reaction, but the overall reaction for what is happening for hydrogen fuel in a fuel cell. Now, here is what does it look like for hydrogen fuel cell. Okay, again, hydrogen is fueled into the fuel cell. At the anode, okay, at the anode, hydrogen will lose electrons to turn into hydrogen ion and electron. Okay, the electron. Of course, electrons is going through the external circuit to produce electricity. That's no surprise because it's a galvanic cell. Now, what's different is the hydrogen 2 plus ion will diffuse through a membrane called a proton exchange membrane here. This is the enlarged version. The hydrogen 2 plus ion, hydrogen plus ion will diffuse from the proton exchange membrane from anode to what? To cathode. Why does it need to be cathode? Because at the cathode, when oxygen gains those 2 electrons, it also needs to combine with the hydrogen ions from the anode. That's why the hydrogen plus ion needs to diffuse from the anode to the cathode so that the oxygen have something to bind with. And eventually, after gaining the electrons and binding with the hydrogen plus ion, oxygen gas will become what? Become water. And water, of course, will be exhausted from the fuel cell as well. So as you can see here in this fuel cell, you keep fueling hydrogen and oxygen, you keep dumping water of the products. So the reaction never runs down as long as you keep fueling what? Fuels and oxidize, and also keep pumping out the waste water. Okay, what's the water? And here is a comparison between fuel cell and burning the fuel directly. We know burning the fuel what? Burning the fuel, you have heat, you have flame. The efficiency is low because a lot of heat will be lost because you have a big flame. Sometimes you cannot confine or take full advantage of the energy released from burning. But if you burn the fuel in a cell, the reaction runs smoothly through the losing and gaining of the reactions in the device. So the reaction is slow and smooth. We don't have flame, and the efficiency is much higher. So the loss of energy will be much lower comparing what? Comparing burning of hydrogen directly. Okay, burning of hydrogen directly. And of course, okay, one of the future of using fuel cell, okay, one of the future of using fuel cell is to use fuel cell in a vehicle, okay, or in fuel cell, we call that, okay, fuel cell vehicles. Okay, one of the fuel cell vehicles which we have already seen used are called hydrogen cars. Okay, here is a picture of a hydrogen fuel cell vehicle, okay, hydrogen car. You can see that, of course, in order to for the cell to work, you have fuel cell pack in which the device to convert the chemical energy into electricity, and you need a hydrogen tank, okay, fuel tank, that means filled with hydrogen. And also inside the cell, you convert the chemical energy into electricity. And then the cell will provide electricity to run the electric motor and DC converter, and also an auxiliary battery that can be used for powering, for example, powering lights and powering the vehicle overall. But here is how a fuel cell can be used is on a vehicle called a hydrogen vehicle. Okay, but there are some challenges for running hydrogen fuel cars. That makes right now you don't see a lot of hydrogen cars near you or everywhere. Okay, it's still a new technology, and because of these challenges, we're solving these challenges as time goes in the future. These are challenges including how do we get hydrogens to consumers, and what are the safety concerns, okay, for storing hydrogen on board, means carrying a big tank of hydrogen. Remember, hydrogens are fuels, they're combustible, they're explosives, and also the cost of the vehicle has to be reasonable, to be affordable to every families. And also, what are the reliability and also durability of fuel cells? Because a car, we're talking about driving quite a few years. So we have to solve these problems too. And here are some websites, and this website is actually keeping updated, talking about the challenges and what have we done about these challenges. Okay, so in this class, we're going to talk about a few of them and what are the common or recent development for addressing these challenges. The first one is, of course, how do we get hydrogens to our customers? Okay, how do we make hydrogen? How do we produce hydrogens? Okay, so far, producing hydrogen still remains a bigger problem because we're high cost process, because the source of hydrogen is still fossil fuels. So that means we're still not we're still relying on fossil fuels, because you need fossil fuels to produce hydrogen. And also this process is endothermic, means you need a lot of energy input to convert fossil fuels into hydrogen gas. Okay, that is why one of the main challenges so far, the cost of hydrogen, even if we're already using hydrogen in hydrogen cars, the cost of hydrogen is relatively high. You can see these two reactions is showing the converting of methane, the natural gas, into hydrogen, and both reactions showing a major input of energy, meaning the reactions is endothermic and requires a lot of energy. That means the cost will increase accordingly. Not to say the cost, we're not even counting the cost of the fuel cell of the fossil fuels themselves. Okay, and here is the device called a reformer. Okay, reformer that converts other type of hydrogen-rich compounds such as methanol to hydrogen as well. Okay, these are some reactions showing you. I don't want to go to details, but the reformer basically converts other hydrogen-rich compounds, still a fuel, for example, methanol, into hydrogen gas. And the reformer also takes energy as well. That means the reaction is still endothermic. And endothermic means you need extra input of energy. And someone raised the concept of putting reformers on board means installing the reformers in your car. So basically you're running on fuel cells, but you're putting in methanol, for example, your car generates. But onboard reformers will add extra cost and maintenance demands to the vehicle. So you're basically not carrying a fuel cell, you're carrying another device called reformer that converts another fuel into hydrogen, Okay, a solution or an alternative route of getting hydrogen if we don't want to use fossil fuels is to get hydrogen from water. Remember, water, our planet is covered with water, even seawater, but we're covered with water. And water contains hydrogen. So basically, we have a limitless supply of hydrogen element. But the thing is, if you want to split hydrogen from a simple compound like water, you also need what? You also need input energy. And the device for splitting water into hydrogen and water is called electrolytic cell. Okay, basically you connect water to a battery, to a higher voltage battery. Okay, actually 9-volt battery can do the job if you watch some videos and you can run the experiment at home. So basically you connect water with a battery, and you're making a different type of cell called electrolytic cell. Okay, electrolytic cell is a device that converts the power of the electricity into chemical energy. Okay, into chemical energy. In this case, it's the chemical energy stored in what? In hydrogen, because you need hydrogen fuel. So basically, the energy in the products of hydrogen is from what? From a battery. Okay, from battery. So you're using energy from a battery to convert that into the fuel energy, hydrogen. Okay, as you can see here, you connect both the positive and negative end of the battery into water, and the water will start bubbling. And in one of the tube, you will get hydrogen. In another tube, you get oxygen. The ratio of these two gases will be 2-to-1 because if you balance the reaction of splitting water into hydrogen and oxygen, the ratio of hydrogen and oxygen is 2-to-1. That is why you get double the volume of hydrogen versus the oxygen. And of course, like we said, burning hydrogen to give water releases energy. That's why we have energy to run the vehicle. And then split water back to the element, the reverse process, needs the same amount of energy. So that means if you want to create hydrogen from water, you need input 249 kilojoule of energy per mole of water by using a certain type of battery. Okay, a certain type of battery. So that is why you're still adding the cost of decomposing water into hydrogen. Okay, now one extra word is electrolytic cell is when you split water into hydrogen and oxygen gas, this process is chemical process. The compound is actually decomposed into the element hydrogen and oxygen. That is different, totally different than you simply boil water. Okay, when you boil water, we're actually breaking the hydrogen bondings. So water molecules get split and they become individual water molecules, the gas, water vapor. But when you apply water to a battery to water, the bubbles are no longer water vapors. The bubbles are actually the element of water, hydrogen and oxygen. Of course, in the topic of splitting the water, one way, instead of using a battery, we can use the sunlight, to split water. And there are some readings for you to do too in this chapter. What are the, how far are we in developing a device called a photoelectric chemical splitting device that use sunlight, which is of course free, to split water into hydrogen and oxygen gas. And you can see that the currently efficiency is very low, less than 15% efficiency. But it is one of the solutions to think about. If we could use sunlight, we need a higher energy sunlight. We know sunlight composed of what? 7 colors. You probably need a lower the lower, shorter wavelengths or higher frequency part of the sunlight in order to split water, energy high enough to split water into hydrogen and oxygen, okay, into hydrogen. And another, and the research level is instead of using sunlight, we can use bio process. Here we call it biophotolysis. Okay, photolysis basically is use some microorganisms. Here is a kind of green algae. They can have a device, they can have enzyme. Okay, their body has produced an enzyme that can split water into hydrogen and oxygen. Okay, into hydrogen and oxygen. Here you can see that this is the solution of the green algae are exposed to light. The light bulb is shading on them, and they can keep exposure to light, and the light will promote the split of oxygen into hydrogen and oxygen, and by, of course, the reaction is catalyzed by the enzymes of these green algae. Okay, green algae. And this is something else, some recent development of how do we produce hydrogen. Okay, how do we produce hydrogen? Another challenge is how do we store, okay, how do we safely store hydrogen gas, and of course carry that hydrogen gas in a driving vehicle. Okay, as a gas, you can see here, hydrogen has a very low density, can takes a lot of space because hydrogen is very extremely light and small molecule. Okay, because hydrogen atom is the smallest one in our periodic table. So, and here example is at sea level and room temperature, hydrogen can occupy a volume of 11 liters per gram. Okay, 1 gram of hydrogen can be that huge volume because it takes a lot of space. Okay, it's a lot of space. And in comparison, 11 gallons of 11 liters of gas has a mass of 8.7 kilograms. You can see that compared to gasoline, because hydrogen is a gas, it takes a big volume. So how do we store a good amount of hydrogen and in a compact and efficient way is another challenge. Okay, one way is to build a cylinder or a tank of hydrogen, which are composed of metal hydrides, because metal hydrides such as lithium hydride can selectively absorb hydrogen gases. Okay, absorb hydrogen gas. So these gases can be pressurized into these tanks and selectively absorbed on these metal hydrides. And of course, when you release the pressure, the hydrogen gas can be released from the metal hydrides. So this is one way of storing hydrogen gas. Instead of just simply adding pressure to liquefy those hydrogen gases, we use metal hydrides to selective to absorb and desorb hydrogen gases. Okay. Now, in this chapter, we have a reading assignment or for discussion assignment that is to watch these two videos, basically video reviews of two brands of hydrogen vehicles. And you can see that the title of these reviews is called The Future. Okay, is hydrogen car really the future? Okay, you can take a look at the review and know what is the current status of regular people using hydrogen cars, and also give you something to think about. Is hydrogen car a real future? Okay, a real future. So that is the first half of chapter 8. We'll stop here. We'll have a short second half to talk about, besides of what we have studied so far of converting chemical energy, no matter in a traditional cell or a fuel cell, but we're only talking about converting chemical energy into what? Into electricity through the transfer of electrons between reactants, through the anode and cathode, transfer of electrons. In the second half of the chapter, we're going to talk about briefly, how do we convert sunlight directly into electricity? And we call those cells photovoltaic cells. Okay, we use the energy from the sun and convert that directly into electricity. Okay, so that is all for the part 1, and we'll See you in part 2. Bye now.